Hello, in this video we're going to go over a rare geometry problem from Putnam Math Competition. This is problem A2 from 1985 Putnam Math Competition. So here is the problem. Let ABC be an acute angled triangle with area 1, rectangle R, R1, R2, R3, R4, inscribed so that R1 and R2 lie on side BC. So I'm going to draw a diagram here. R3 lies on side AC and R4 lies on side AB. Similarly, a rectangle S is formed inscribed in A, R3, R4, so this would be rectangle S, with two vertices on side R3, R4, and the other two vertices on AR3 and AR4, and we want to find the maximum area of S plus R. What is the maximum area over all possible choices of the rectangles and the triangle? Okay, so that is the question. So in general, when you want to find areas, there are usually two ways of finding areas. Either you take your region, and if it's a complicated region, you slice it up into smaller regions that are known regions, or you complete that region into a larger region which is simpler, and then you subtract the complement. In this case, the region that they gave us, these two rectangles, are pretty simple. However, if you were to write down the areas, it would depend on too many variables. I mean, it is possible to do it that way, but I would rather avoid the too many variables and try something slightly different. So if you look at the area, that the complement of this area, we have 5 different triangles, 1, 2, 3, 4, and 5. The top triangle is similar to the original triangle, which means if I know one side of that, the ratio of one side of this to the entire thing, then we would be able to find the area of that triangle. So let's say the height of this triangle is x. If the height of the original triangle ABC is h, then the area would be x over h squared. So if I call this one h, then the area of this region would be x over h squared times the area of ABC, because they're similar, and the area of ABC is 1, so that would be x squared over h squared. Now there are 4 more triangles left. These 4 more triangles are also can be combined to get similar triangles. So if I draw a segment parallel to segment AC, I get this triangle. Portion of this triangle, the yellow portion, is congruent to this one. So that means this area, the two triangles, that if I add them, I get also a similar triangle to the original one. So if I call this height y and this height z, the area of the red triangle and the area of the green triangle right here can be also evaluated in terms of y and h, and y and z and h. So the total area of ABC minus S minus R minus area of R minus area of S is equal to x over h squared plus y over h squared plus z over h squared. So the area of R plus the area of S is going to be, area of ABC is 1, so it's 1 minus x squared plus y squared plus z squared divided by h squared, and h is x plus y plus z, and then we're going to have to square that. Now we are told to find the maximum possible value of this area. In other words, we are trying to minimize x squared plus y squared plus z squared over x plus y plus z squared. So we could use one of these inequalities. It's called arithmetic mean, square root mean. So square root of x squared plus y squared plus z squared over 3 is greater than or equal to x plus y plus z over 3. We are going to square both sides. We get x squared plus y squared plus z squared over 3 is greater than or equal to x plus y plus z all squared over 9. And if we divide by x plus y plus z squared, we get x squared plus y squared plus z squared divided by x plus y plus z squared is greater than or equal to 3/9, which is 1/3. So what does that mean? It means the area of R plus the area of S, which is 1 minus this quantity, x squared plus y squared plus z squared over x plus y plus z squared, is less than or equal to 1 minus 1/3, which is 2/3. So these two areas add up to something less than or equal to 2/3. Now, do we have equality? Yes, we can get equality when we know for arithmetic mean, square root mean inequality. Equality happens when x, y, z are the same. So when x and y and z are all the same. And that obviously can happen. We can choose our triangle, just basically any arbitrary triangle of area 1. Make sure that the heights are equal, and then you would get an area of 2/3. So the maximum is exactly 2/3. And that brings me to the end of this video. So I will see you in the next video.